for joining today's webinar, Accelerating Verification and Certification for Safety Critical Software with Cantata and TRACE32. I'm Silvia Sanchez, Marketing Executive at QA Systems, and today we're going to explore how development teams can streamline verification activities, improve coverage, and generate certification-ready evidence for safety-critical software. You'll see how Cantata and TRACE32 work together to simplify verification from instruction set simulation through to real hardware testing. We're also pleased to have u-blox with us, who will share insight from a real-world project. During today's session, we are going to dive into the verification challenges in safety-critical software, how Cantata and TRACE32 work together. We're going to have this real-world experience from u-blox, and we'll look at verification workflows from simulation to hardware. This will be followed by a live Q&A session with our experts. And before we start, I'll give you a few housekeeping notes for keep this webinar running. So all attendees will remain muted throughout the webinar, and questions can be submitted at any time using the question panel that you can see on the right-hand side of your screen. We're going to try to answer as many questions as possible during the Q&A session at the end, but if we don't get the time, don't worry, we'll follow you via email. Without further ado, I would like to get started, so please join me in welcoming Ioannis Anagnostopoulos. He is a senior embedded software engineer and line manager at u-blox. He will join us for the first part of today's webinar.
Hello, everyone, and thank you for having me in this webinar. I'm Ioannis. I have been leading a software team in the functional safety program of u-blox for about 2.5 years. I will now present you a case study about the unit and integration testing phase of the ASIL-B safe measurement engine product of u-blox, the A9 chip, which is featuring the Cantata and TRACE32 tools as part of the test environment setup. So let's start, and let's start with the testing process inputs. What do we have here? Starting, we have software under test. Of course, this is the source code in C that we want to test. So we actually want to test expected functionality according to requirements. Test scope can be decided based on test strategy, can vary from function, files, also integrated items. So many files integrated together. This is what we want to test. Then we have test scripts. Test scripts are files, again in C, that mostly in C, at least in our case, that are implementing the test sequence for the chosen software under test, mainly according to a test specification that is also developed to test the expected functionality. The tests are executed in a target test environment we choose and we set up. And last but not least, we have the deployment. So we need some kind of a glue. We want to combine together the software under test with the test scripts, compile them, link them together, and produce an executable which is compatible with the test environment that we have chosen. The output test result is also configured based on the test environment type. So it's everyone basically set up based on our needs. Then you can see a list of the tools and their specific versions used, including, of course, Cantata and TRACE32, and also the ARM compiler for functional safety products, which is used for the deployment, for compiling and linking everything together. From this testing process, we expect to get test results and code coverage reports in a human readable format, which are ready to be processed, reviewed, and also put under configuration management. So in this next slide, you can see a very simplified diagram of the test environment setup in our product. On the left, you can see the test development environment, which is mainly Cantata. On the right, we can see the target test environment, which is a TRACE32 tool and basically the ARM instruction set simulator, which is available in TRACE32. They both exist in a native or a virtualized system, depending on your needs. The test development and the test execution process goes something like this. So I also use a laser pointer. Hopefully you can see it. So we start, of course, we here in the middle, we have the software under test source code that we want to test, either it's production code or something experimental. On the Cantata side, we have developed, or we developed test scripts to test this source code. And together with the deployment, we compile and link everything using the using a compiler, specifically the ARM compiler for functional safety in this case. All this produce an executable which is in a proper format to be executed in the instruction set simulator, which resides in TRACE32. After the execution, TRACE32 is producing an output, which is called here a multiplexed output, which is actually an output in a binary format, which is not human readable. It's something we can say decoded, encoded. Encoded output, and this output then is fed back to the Cantata tool, which includes a tool to demultiplex this output and produce then test results and code coverage reports that are human readable. They can be post-processed, reviewed, or version controlled eventually. And let's see now some key takeaways from this test approach. Why should we use the instruction set simulator instead of real hardware? First of all, with a simulator, you have no physical dependencies with the target hardware. So all of the test process can be performed in your native or a virtualized environment, Linux, Windows, or another operating system, or anything that you can set up these tools in. And by that, there's with no real hardware, you of course don't have hardware resource restrictions to be considered, like CPU performance or available memory. Something else that can be enabled with this setup is debugging. Debugging in hardware and in a real system, in real-time systems, is most of the times challenging. But in this setup, you have the ability to debug your source code, combined even with the test scripts in a more native environment. And of course, not having the real hardware, but being able to test your source code accelerates the test development process itself, especially in cases when the real hardware is not yet available. And last but not least, we have CI. CI is nowadays everywhere. Having this test set up in a software kind of environment, we do not need any hardware setup to proceed with the testing process. Everything can be done with, for example, with a Docker container that is set up to include all the tools mentioned, and can be triggered with a CI and enable test automation. However, this approach is not ideal. I mean, the real hardware is the real product, and sometimes we need the real hardware. As you can imagine, the simulator is just a simulator. I mean, it oversimplifies hardware components, and especially in real-time systems, you do not have the real-time concept anymore. So sometimes test results can be misinterpreted or are not showing the full picture. And so this simulation should be used with caution, and the test scope and the test strategy should be properly defined. Also, with the hardware, you you almost certainly have a hardware-software interface. In order to simulate this, you need to properly stub or mock it, which requires some additional effort. And when there's no time to invest in something like this, you probably will need the real hardware to do so, which also gives a benefit to test the actual hardware-software interface and how it's defined. So with this, I conclude the case study presentation. Thank you all for your attention.
Thank you very much, Ioannis. Now we're going to move over to Mohammed Ayub. He's a software developer from Lauterbach, and he will introduce TRACE32 and demonstrate how these will support verification workflows from simulation through real hardware.
Hello, everyone. I think you can, yeah. Hello, everyone, and welcome again to this joint webinar. In the scope of this webinar, I will be presenting TRACE32 and, in general, Lauterbach hardware and software tools, and especially the automation frameworks and how TRACE32 is integrated with Cantata, whether we're talking about instruction set simulator or real hardware. So when we talk about debugging or hardware-based debugging of chip trace, target analysis, TRACE32 is the industry standard. It provides an identical user interface and scripting environment, whether you are performing early virtual prototyping or validating real silicon in production. So TRACE32 PowerView debug software. This is the single unified interface that developers and testers will interact with, bringing all system diagnostics into one cohesive, say, cockpit. This interface displays core registers, system memory maps, compiler symbol tables, and real-time execution timelines simultaneously. So this total visibility allows us to look beneath the surface during automated verification passes. Okay, so for the hardware side of things, the TRACE32 module architecture, oops, okay. So for the hardware side, the TRACE32 modular architecture separates the debug engine from the target interface. Universal debug modules handle high-speed communication with the host PC via USB or LAN, while off-chip trace samples the trace results from the trace ports without interrupting the execution. So what does this mean actually for the development team or test team? So full support for heterogeneous multi-core debugging and off-chip tracing, the broadest yet for RTOS and hypervisor awareness, a dedicated tool, qualification support kits for functional safety certifications across all relevant standards. Also, this will be subject of our next slide, but TRACE32 make sure to support the whole product lifecycle from cloud-based virtual chips to real silicon in the field, de facto industry standards. One of the strongest architectural advantages of this ecosystem is its lifecycle coverage, starting with SOC verification. Before physical silicon even exists, TRACE32 connects directly to hardware emulators and virtual targets using standard interfaces like GTL or MCD APIs. Then it transitions smoothly into early software development where your software teams can write or test driver code on cloud-based targets, aka virtual targets, or performant instruction set simulators using the exact same TRACE32 debugger. When the physical ship arrives during prototyping and testing, we transition from the virtual environments or connections to physical debug cables via JTAG, serial wire debug, PCIe. The final stage is when in field testing, we can also interface directly with the physical ECU over USB or XCP protocols. Because TRACE32 sits across every single phase, as we just seen, your team can reuse the exact same scripts, tests, and automation setups from the simulator phase all the way to physical road testing, which obviously dramatically decreases the bring up times and accelerates the time to market. To sum up this slide, TRACE32 is not just software, hardware, or just hardware. It is a unified standard ecosystem that combines high performance debug and trace hardware with a powerful software cockpit to handle safety critical multi-core embedded environment. So moving on to the integration interfaces, and now we'll be looking at how we can automate this toolchain. So TRACE32 is more than just an interactive graphical debugger. It features highly robust integration interfaces designed to slot directly into automated test frameworks and continuous integration pipelines. So we'll be starting with the native automation layer, which is the practice scripting language. Oops. Yeah, I'm spoiling the presentation. Okay, TRACE32 is practice layer is recognized by its .cmm file extension. This is a low-level, high-performance execution engine that allows you to automate target initializations directly, manipulate the CPU registers, configure complex breakpoints, extract memory buffers, and handle all sorts of other things, software or hardware. So a simple syntax is a bring up for the S32K3 from NXP, just CPU selection, system up, data.load.l for loading the program, and go.direct to go to certain symbols. This allows to fully automate your work. So moving on to a integration with CAPI interface, which is used mostly for integrating with legacy or compiled external test applications. So TRACE32 exports a raw socket-based CAPI that communicates via UDP or TCP or shared memory. This interface is optimized for high throughput headless test execution. And yeah, so you can, for example, attach to the debugger with T32 init and the T32 attach APIs. You can later, for example, check the processor's execution state with T32 get state or perform low-level block transfers using memory read and memory write API hooks. More details can be found in the documentation below, and example code also and pre-built examples can be found and tested under the T32 demo installation folder stated below. So now we're moving to beyond proprietary interfaces introduced by TRACE32. TRACE32 also embraces open industry standards such as JDP. It can operate as a GDB remote serial, It can start acting as a back-end server or a front-end client to bridge third-party environments like VS Code or Eclipse to the underlying hardware for complex heterogeneous multi-core SOCs. You can also export the standardized MCD API. This is particularly important for multi-core systems, allowing synchronized run control, step lock-in, tracing across completely different core architectures residing on the same silicon. So yeah, ISS and migration to real hardware. Having explored how to control the debugger, let's look at how we can execute unit tests early in the design cycle by utilizing virtual environment before crossing the physical gap to real hardware. So starting with virtual prototyping, the Lauterbach instruction stimulator allows you to run, debug, and profile your exact target binary directly on a host development PC without the need of any physical hardware. Talking about debug modules and probes. So the ISS accurately simulates instruction execution, caches, memory protection units, and internal timers for a wide range of architectures. You can quite simulate to a certain level also peripherals, and yeah. It also allows you to integrate your own custom peripheral models and comes with certified tool qualification support kits, as we already mentioned, to ensure compliance with strict safety standards from the day one of development. Now, migrating to real hardware. With the simulator, while it is invaluable to early verification, migration to real silicon introduce real hard-world physical challenges. Hardware pipeline stalls, cache misses, complex clock tree setups, and unpredictable, say, peripheral timings. TRACE32 bridges this physical gap by maintaining absolute script compatibility environment, because the scripting engine and remote automation logic are completely hardware agnostic. The same test sequence you will be validating in the simulator can be deployed directly into or onto a physical target, or later on your ECU via reference initialization frameworks. Okay, so moving on to the Cantata integration and already presented case study by Ioannis. So the integration strategy is divided, say, into 4 or 5 main steps to achieve automated non-intrusive software verification standards like ISO. So Cantata starts by performing source level instrumentation, injecting software probes and allocating a dedicated coverage bitmap array inside the application's memory map. TRACE32 then takes the resultant instrumented ELF binary, loads it into the target, and synchronizes the complete compiler symbol tables. Once that's been done, the target executes at full speed, while TRACE32 keep passively monitoring core execution in the background via non-intrusive pollen. Upon reaching the test suite's terminal exit routine, TRACE32 then intercepts the execution marker and halts the processor hardware pipeline. And finally, TRACE32 perform a direct memory upload, extracting the raw coverage directly from memory into the stream for final reporting and for the multiplexing, or say by Cantata. So the automation framework implementation, this deploy provides a turnkey automation driven by two vital control elements, which are the T32 PL or bus per wrapper script that programmatically spawns the TRACE32 instance. It controls the execution paths and monitors the target's output streams. The second script is the T32.ref, which is a baseline practice initialization script that establishes target clock settings, configures memory maps, and manages the automated buffer extraction loops. By combining these or both scripts with Cantata's native buffered output mechanism, you can run complete regression test suits with a simple terminal command. A few notes which depend on your application, the architecture you're working with, if you're working with an instruction set simulator, virtual targets, or real hardware, you might need to slightly update these wrapper scripts. Obviously, we have reference scripts under demo under our demo directory. So to wrap this up, by combining Cantata's test generation with the execution control and tracking power of TRACE32, we can eliminate manual bottlenecks and fulfill rigorous functional safety verification requirements. This is a small introduction to what TRACE32 can do in the scope of this webinar, but can do way more. Yeah, that's all from my side. Sylvia.
Thank you very much, Mohammed. Now I would like to welcome Andreas Szczepanski. He is the CEO at QA Systems, and he'll be followed by Heydar Akbulu, Field Applications Engineer, who will show us how Cantata complements TRACE32 by enabling automated testing, coverage analysis, and certification-ready evidence generation.
Thank you, Sylvia. Good morning, all together. I would like to give a very short overview about the QA systems itself and our portfolio, and then we step into the product itself. So maybe for those who know us, we are always very well known about our racing car and about our racing activities. So the car is real. I drive that car. I'm a race driver. That's the job I do apart from QA systems. So there's a real story behind, but that's not the focus for today. So I founded QA Systems in 1996. We have started mainly as a reseller for testing tools, especially static testing and dynamic testing in the safety-related markets. The big change was then in 2011 and 2012, where we have been able to purchase a testing product that was at that time Cantata. We purchased that from a consulting company in the UK, and from that point we changed completely our business model and strategy away from a reseller towards an own product vendor. We supported that by a foundation of separate daughter companies. For example, in Italy, we started then the US activities. We have since 2020 a daughter company in Vietnam, which is mainly as a second development office. And in India some years ago, where we had another sales office and support office. Now, product-wise, we launched in 2021 a new static analysis product called QMISRA, together with our 25th years anniversary. And in the last years, we had built a new product called Cantata Hybrid, what I tell you shortly about. And in 2025, last year, we launched a completely new product, completely independent from this market. That's an AI controller. That's an AI gateway to handle your AI agents within a company. Now, this year, we are in the party modus. We have our 30-year anniversary. And yeah, from time to time, we do some business, but the rest of the year, we are celebrating our activities. Now, as a short overview, we have Cantata, which is a unit test framework. I explained a little bit more. We have Cantata Hybrid, which is a slightly derived from Cantata, mainly focused for Google test. We have the static analysis, QMISRA, what we will not talk about today, and also the AI controller. So if you would like to receive more information about QMISRA and AI controller, send us an email. Now, oh, that was too fast. Software testing with Cantata. Cantata is an unit and integration test framework, mainly built to help you with doing unit tests and integration tests, as you see here on the right side of the V model. It's built on Eclipse, but we also have very good integrations into Visual Studio, or nowadays, of course, Visual Studio Code, which is a very important platform. We launched as a first vendor in that area a complete AI-assisted integration. That means you can work with your own and preferred AI agent to let Cantata do the work with you. This is not part of the presentation today, as we only have a very short overview of Cantata. But if you are interested in that, also here, let us know, and we can always do another presentation for you. Mainly, the main features of Cantata itself is, of course, the generate the code coverage. We have a CI/CD integration. We can link the requirements to your tests, which is very important. And we can, of course, support multi-target test frameworks. And that's how we also support regression testing. And very important, as we are mainly in the safety critical market, all our products are certified by SGS TÜV against all major safety standards, ISO 26262, IEC 61508, and so on. So more or less all important standards are covered. Now I talked about Cantata Hybrid. Cantata Hybrid is, as I said, a slightly changed version of Cantata. And the positive aspect with Cantata Hybrid is that it can read your Google tests. You don't need to change your Google tests. It can read exactly your Google tests, how you write it. The benefit for that is Cantata Hybrid is a certified test environment. That means we can not only generate certifiable output in case of code coverage, we can also show the test evidence output in a certified way. That means that opens the world for you to use Google Test in all safety-related projects, but then you just use Cantata Hybrid during any time of your project and generate the certified output what you need to receive a certification by yourself once you are using that in a safety related project. So Cantata Hybrid is nothing more as the certification solution for Google Test. It's based on Cantata because it's quite similar. Google Test is quite similar to Cantata. So both versions, so Cantata and Cantata Hybrid, will therefore, of course, work with Lauterbach emulators. And that's the next step. All Cantata versions are integrated with various Lauterbach hardware and software. For example, the simulator, what u-blox talked before. But we also have the integrations with all other devices from Lauterbach. The big advantage is the interface, how to run your unit test or how to generate your code coverage with Cantata stays always the same. It's just a marginal way how we talk to the target, and that's how what we call a deployment. That's the very short overview of Cantata and what we are doing. And my colleague will show you a little bit more about the product itself.
Thank you. So next, you will see how all of this works in the eyes of a Cantata user who is working with a target deployment that connects all nodes mentioned before, such as compiling, linking, debugging, and of course, testing. And as Andreas said, how testing procedures are not affected by the change of this deployment. So for the sake of demonstration, I will close my camera and share my screen. Hello everyone. In today's demonstration, we will take a look at Cantata, how it works and how it can be integrated into your build environment when needed. On the left side of your screen, you see two main sections. Project Explorer, which is similar to Windows Explorer. It allows you to browse your project structure, including both the source files and the Cantata specific files related with your project. And the next one is Test Explorer, which is focused more on test scripts and test cases as well as test results of our test script executions. This is also the section we use for designing our test structure. Here in today's demonstration, I have two projects and we will start with the host one. Inside it, I have a blood pressure C file. And if you look at this source file, you can see I have a blood pressure check function, which is using systolic and diastolic variables. And we have an if-else statement inside it. And we are calling different functions depending on the status of this statement. Now, I would like to take your attention on one thing. Here I have definition of high pressure check and low pressure check functions, but in my source file, I don't have the definition of sound alarm. So existence of sound alarm is present to Cantata, but I am not giving it behavior of it yet. So let's see how Cantata will cope with this situation. To see this, let's create our first test script, and I'm one-clicking the source file, and inside test properties, we just click generate test script. Here, you can see we have some options to select, and these options will let us design what kind of test script we would like to create. The first is the type. Of course, it's function selected right now because I'm working in a C file. And the second one is initial test cases. Initial test cases means, do I want Cantata's help as a first step when I'm creating the test script? If I select none, it means I want Cantata to create an empty test script, which I can create test cases on top of each other to reach my coverage expectations manually. If I select test case per function, Cantata will create one test case for each of my function, and I can add more test cases as I need based on my requirements or coverage expectations again. And the last one is auto test. Now, the auto test option is using Cantata's algorithm, and when you select that, Cantata will read your code, analyze it, and create test cases automatically based on your coverage rule set expectations. Depending on your code complexity, it can give you weeks or even months of work as a jump start in a couple of minutes. But we will start with none at the beginning of our demonstration, then we will switch to autotest later on. So the last option here is the coverage rule set. This is one of the features I really like about Cantata. Imagine that I'm in your company and you told me to test this source file according to automotive, standard, and ASIL D level, and I have no idea which coverage rule set I need to apply. But good news, Cantata knows. So I can click this drop-down menu and select the standard and then level of it. Mine was automotive, so I will select this one and click next. When I click next, we are in the call interface control section. Cantata here created stop for sound alarm and wrappers for high pressure check and low pressure check functions. As we have limited time in today's demonstration, I won't go in too much detail regarding stop and wrapper features. But basically, it created a stop for sound alarm so I can test existence of the function under certain circumstances, because I didn't give the definition of the function, so it doesn't know the behavior of it. And then it created wrappers for high pressure check and low pressure check functions so that I can control and test their behaviors under different scenarios. Let's click finish and see how test cases look. Here, to create our first test case, in the test case node, I can right click and add one test case. Here I can select the function I want to test and then click finish, and we have an empty test case for now. Before designing our test case, I would like to show you one thing. In here you see a node named SUT. If I expand here, there is an item with the same name of my source file, and if I click here, you can see all sections are red in coverage viewer. That means I am not covering any section yet in my tested unit, with the test cases I have, of course. So take your attention on high pressure check function, which is all red right now, and we change it by adding, designing our test scenario here. In test case editor, we have two main sections. The first one is calls expected during test execution. Do I want any other function to be called when I'm testing high pressure check? When we look at the function again, you can see when you execute high pressure check, there is no other function calls. Therefore, this section will be empty. The next one is test case data and flow. This is the area where I call you create your story. What do you want to see if it is happening or not, when what happened? You can design test preconditions, set global data, you can set variables inside or outside of your functions. You can even control the static variables here, and you can call a function exactly how you want to call it. So in today's demo, I want to call it with these inputs, 70 and 80 for this systolic and diastolic, and I'm checking if it is returning 1 or not. To test this, I need to run this test script, and for that we are in the test script here, and then I'm clicking run, and we get the test results here. Now if you notice, I get a pass for the test case I created, but a fail for the test script. See what happened coverage viewer, and you can see high pressure check now has greens, but still there are some sections red. Why? Because the test case I have does not cover the functions all behaviors, so I need to add more test cases. At this point, I would like to show you one more functionality of this coverage viewer. In QA systems, we believe a good testing tool should not just give you the results of test executions. It should also help you regarding what to do next. So in here, if I click the yellow section, Cantata tells me one of two outcomes has been executed for this function. So I need to create at least one test case to cover the rest of it. Okay, now I know I need to add one more test case for high pressure check, but instead of doing that, I will use autotest this time. Again, clicking the source file, generate test script, this time clicking autotest and click select the same standard as we selected before and click finish. Now Cantata created autotest with 9 test cases. And if you look at the blood pressure check test cases or test cases related to blood pressure check function, you see the expected calls are different. Why? Because in here, depending on the variables here, the blood pressure check will get different behaviors. So these or these can be true. So there are 3 behaviors of blood pressure check, and Cantata automatically recognized that. And depending on the statement here, there are different function calls, and again Cantata recognized them automatically by itself. So let's run the test script. And you can see now all got pass, and in the SUT section of my source file, I got green in all sections. So when you execute a test script in Cantata, there are 3 outputs. The first one is the coverage viewer that we talked already. The next one is the HTML report. HTML report, in here you can see all test cases, what was used as an input and what was the check and such. And then at the end of it, there will be one node named coverage rule set. If you remember, I just selected the standard and let the Cantata decide regarding coverage rule set. And here Cantata selected them automatically regarding the standard I selected. The last one is the CTR report. Basically, content is same with the HTML one, but this one is the certified output of ours. Now, imagine in a scenario where the user want to use or user want to run the test on target, or even a simulator environment, or user want to use their own cross-compiler environment. So how Cantata can answer this need? In Cantata, we have a feature named target deployment. Target deployment basically means teaching Cantata how to use your environment. Before demonstrating that, I would like to show you in the host project what happens when I clicked run for my test script. As you can see, Cantata compiled test driver with GCC, linked it with GCC, and executed in host environment. Now, if we switch to target project, I have a similar source file and similar test script in here. But this time in the target deployment selection, we have the deployment specifically created for this purpose. And in this example, we are running ARM.NIB GCC, and then we are using TRACE32 for our debugging purposes. So this deployment knows all of these procedures. So if I click run, you see the execution of the test script is a bit different. So TRACE32 popped up, it did its job, and then closed automatically. Again, I got the same results, and if I click the SUT again, you can see all of them are green. So let's see the console output. As you notice, console is also different because now we are compiling with ARM.NIB GCC instead of GCC. Same goes for linking. We are using ARM.NIB GCC, and for debugging and running it, we are using TRACE32 in here. Now I would like to take your attention on one thing. As you saw in the screen, I did not open any other tool. I was just staying inside Cantata all the time, and Cantata was calling the necessary executables automatically in the background. So without even switching in between, you can stay in Cantata and teach Cantata how to use your build environment with target deployment, and then Cantata can take care of the rest. Of course, this can also be integrated into your continuous integration pipeline. So even without opening Cantata at all, you can execute regression testing by using simple commands from Cantata. So let's minimize this and open a prompt. Here we are in the target project, as you can see. And inside this project, I'm just issuing some commands. So make clean, the first command, I'm just cleaning the previous execution. And as you can see, my test driver being compiled, linked, and executed, TRACE32 popped up, did its job, closed again, and all of this done without even opening Cantata. So this was it for today's demonstration. If you have any questions, please feel free to ask during Q&A section, and I will be happy to answer all of that. Thank you very much.
Thank you very much, Heather. Now we will move into our Q&A session. So if you have any questions that came during the webinar, please put them on the question box on your right-hand side of the window. We're going to allow some time for you to do so. And in the meantime, let's welcome our presenters back for the discussion. Go Andreas, Ioannis, Mohammed, and Heather. Thank you very much. All right, so I got an initial question here, which I believe is addressed to Lauterbach. The question says, when running unit tests on modern multi-core or lockstep automotive architectures, how does TRACE32 automation handle core synchronization? If one course hits a breakpoint, how do you prevent the other course from continuing to execute, skewing the test results?
Okay, thank you, Silva. So basically, you can't rely on site software routines to halt a multi-core SOC. The latency of an IPC command is too much, really, too slow. So creating severe cores skew where unrelated cores execute thousands more instructions than what the test boundary is set to. So TRACE32 mitigates this by directly programming the silicon's native hardware debug infrastructure, such as the core side CTM, or say, for example, for Infineon, there's the OCDS and ECT. The exact cycle of breakpoint trips on a core A, for example, a physical signal fires across the whole die to the debug units of core B, C, and D, etc., freezing all cores simultaneously. From our side, also, we provide SMP, AMP, and EMP solutions. SMP is for symmetric multi processing for similar cores, similar architectures, AMP for different cores, and EMP is for even so controlling instances with different architectures and OS. So that's why our TRACE32 handles the multi-core automation tests.
Perfect. Thank you very much, Mohammed. I have cherry-picked another question, which is regarding to Cantata. And the question says, can Cantata be introduced into an existing AUTOSAR or legacy embedded project without significant changes to the code base? That is for you, Heather.
Of course, no matter if you start with Cantata from the beginning or add Cantata to your real environment in the later stage of deployment, you can easily do that without changing your code at all. You can just create a target deployment, and then the rest will be done by Cantata. So no any other change required.
Perfect. Thank you very much. The next question says, what are the latency and performance trade-off of driving the test pipeline via the Python interface compared to executing native practice scripting directly?
The Python latency bottleneck, let's say, every command sent via the Lauterbach TRACE32 RCL must be obviously serialized and transmitted across the IPC protocol or layer, such as TCP or UDP or shared memory. to the active trace32 instance, so processed and then returned. If you write, say, a tight loop in Python, which tries to, say, read a target registers an extensive amount of times, say 500 times or so, the IPC round trip overhead will heavily penalize the test suite throughput. So the solution really is to use a hybrid architecture between the Python automation and the practice zero overhead advantage. So leveraging the Python at the orchestration layer and calling the script for handling the performance critical workloads like offloading, target initialization, flash programming, initialization of memory, etc., etc. Hopefully that answers the question.
Thank you very much. One more question. Does Cantata have a limitation regarding these integrations, Heider?
So there isn't really a limitation on Cantata side when it comes to tool integrations, because Cantata's deployment feature is designed to use your existing build. So your build environment copied by Cantata exactly as it does its normal work. As a result, any build procedure that works in your existing setup will work same with the Cantata integration as well. So there is no additional limitations from Cantata side.
When migrating test cases from a host-based instruction set simulator or an ISS to physical target hardware, what are the most common structural or timing anomalies that cause a test to pass in simulation but fail on chip?
Okay, good. That's for me, I guess. So first of all, the memory architecture and wait states. The instruction set simulator configuration typically treats memory spaces as flat instantaneous arrays with basically zero access latency. On the other hand, physical microcontrollers introduce hardware flash wait states, cache messes, TCM, which is tightly coupled memory arbitration. This significantly can alter executing timing, which can invalidate some time-sensitive communication drivers. So also asynchronous peripherals and clock domains are not, or rather can't be simulated exactly as they would act in real target hardware. Maybe another thing to mention is the hardware initializations, watchdogs, which need to be served in a real hardware, also can have an impact on switching from the ISS to physical actual hardware.
Perfect. Thank you very much, Mohammed. Let's move into the next question, which is addressed to Heider because it's related to Cantata. It says, do you support symbolic links when Cantata is used in a version control system?
Yes, of course. As long as Cantata can access the actual source files either directly or through the symbolic link, then it's fine by Cantata.
Perfect. Thank you very much. I got one more question here that says, does it just use the user's build environment executables directly, or is there any other information Cantata gets when generating deployments? Again, it's for you, Heider.
Yeah, okay, that's a great question. The answer is that Cantata doesn't just use the build executables when generating the deployment, it also learns to build the build process itself. Every project has its own build commands with specific compiler and linker arguments, including paths, definitions, and other options that are essential for building the software correctly. Cantata uses all of these informations so that it can ensure that the build procedure is exactly same with the user's original environment.
Lovely, thank you very much. I think I got a chance for one more that reads, let's choose one for Lauterbach. So it says, what is the strategy for qualifying TRACE32 as a trusted tool within an ASIL or ASIL-D compliance workflow?
So basically, you don't have to, or the customers shouldn't have to qualify TRACE32 completely from scratch. Lauterbach's internal software development life cycles are always or regularly audited and certified, providing an official certificate confirming that TRACE32 is in structure or structurally fit for use in safety critical software development up to ASIL-D. They also mentioned TQSK, which is the tool qualification support kit, is intended for development teams because we can't provide a static support kit. Every development environment features a unique combination of compilers, host PCs, target boards, layout, and that's why Lauterbach provides this support kit, which is localized automated regression test suite.
Perfect, thank you very much. Unfortunately, we're reaching the end of our webinar. Thank you everyone who joined us today. Please note that if we didn't get to your question today, our team will follow up with an email with the answer. Special thanks to our panelists, Andreas, Ioannis, Mohammed, and Haider for sharing your expertise and experience. And please know that also with our follow-up, you receive the recording of this webinar, as well as supporting resources and details on how to arrange a follow-up discussion with our expert, should you wish to learn more. Thank you very much for being here today. I hope you find this session useful and enjoy the rest of your day. Thank you.